Hello everyone. So we are back again with our second session of the boot camp that is about understanding the convolutional neural networks. So yesterday's session we had Archita with us. In today's sessions we are gonna have Shashank with us. So Shashank has a background of a BBA, yet he's working in the field of data science and deep learning. Currently, he is working as a, I guess, currently as a junior machine learning engineer at Omdena, and he's a pass out from MSIT. So let's have him on the stage today, and let's see what insightful sessions are we gonna have today.
Hi everybody. I'm Shashank. So uh, I hope all of you can hear me. So I did my data science bootcamp from Byte Academy post my BBA, and I've interned at a few places. Did a research internship as well, and got a job offer at Big Vision LLC, which I had to leave because of certain reasons. So I've interned in computer vision and CNN as well. So it's a pleasure to have you all here, and we'll be watching a video and some explanation, and then we'll go through some slides, and post that we'll apply the code and the concepts that we had learned during the whole process.
So okay, guys. So Shashank would be taking on the stage now.
I'll just skip forward a bit so we can get to the basics first. Yeah, so this is a very basic part of what a convolutional neural network does is it sees, I mean, the computer has to see whether the object here is an X or O. So for that, the computer learns from many examples that it already has, and predicts on unlabeled data. So here we have two images, and we are going to run a convolutional neural network through those images. Now I'll just describe you briefly, and later on we'll be going through slides of it as well, of what a convolution is. So a convolution is a square, a smaller matrix over the big matrix. Let's say a square which is 3 by 3, and it uh, a number is assigned, and it multiplies, and there's a summation, and from that the algorithm learns which feature of this image, let's say a line, or something which is similar to a zero, is there present, and based on that the computer learns and predicts. So here there are some operations that we can do, and some invariances which we have to take into account when we do the convolution. So we can shift the position, we can rotate, or we can we have to learn the object in question, if it is rotated or whatever shape it is in. Right. So what the computer does is we assign numbers to different parts of the image. So we can see here the negative ones are the black part and the ones are the white part. So let's say it's an image of a dog or a human face. So for different uh, parts of the face, different colors of the face, different numbers are assigned, mostly from 0 to 256, and in RGB, red, green, and blue colors. So 0 to 255, and here we have only two, so it's easier to understand. And like I was saying, if the image is shifted or if there's some irregularities, invariances, spatial invariances, so we need to see how to bring that into account. And that's what we are discussing here. So the algorithm would find parts of the convolution which are similar in the two different images and decide. So we can see the X center part of it here and the different diagonals for the X. So I just want to go back and share. So here the ones matches with the whites here and the minus ones with the blacks, and so the computer goes through the image, if it is if there's some rotation and all, and sees how the 3 by 3 matches with the different 3 by 3s in the bigger image, in the bigger matrix, and with the numbers actually. The computer would it knows the language of numbers. Yeah. Now the smaller matrices are called kernels, and they filter through the process is called filtering. So they filter through the whole image and make a feature map. So this is a simple maths that we do for an image like this. So we want the computer to understand the maths for a particular part of the image. So if it is at the right place at the 1, we get a 1. And if it is at -1 and -1, then also we get a 1. Similarly, the computer will multiply, the algorithms will multiply the ones and minus ones or whatever number in a more complicated image, and then divide it by, yeah. So the whole 3 by 3 here is represented as 1 here. Similarly, the computer will filter through, like I said before, on different parts of the image, on the bigger image through the smaller kernel, and perform the same calculations. Now imagine different images with x's, so the computer would know where the calculations add up to 0.55, like in this case, or to 1, and that helps the computer later to learn a more complicated feature. Like right now it might just learn an edge, but later on in we'll be discussing how the convolution would again and again make up layers to learn the features, and later on it can detect even more complicated features like eyes and ears. So this is the outcome of doing the filtering by a 3 by 3 kernel on this 9 by 9 image. So the smaller matrix goes over the larger matrix and gives this output. So by this we are actually reducing the calculation which we'll be making at the end and learning the features. So we can see these numbers, these are the higher numbers here, the numbers which are more in you know, the value of the numbers is greater, and they are all across the diagonal. So this is how the computer would learn that it's a diagonal. So ultimately what we are doing is we are using the convolutions to find out the numbers at different points in uh, the feature map, and we are getting a map of all the features that are there in the form of numbers, and we are stacking them. So from an image we have gotten numbers which are stacked in a particular way. So our filter, our kernel, has convolved over the whole image to get a convolution layer. Now I'll explain it to you what a stride is. And a stride is the number of steps that we would take. Like in this case, we might, let's say, uh, here we might just go one, we might just shift one to the right and then do the convolution, and then one to the right and then do the convolution. So that's called a stride of one. A stride of two means that we go two to the right and then do a convolution. And here we are taking the maximum value by dividing. uh, yeah sorry, we are just taking the maximum value here. Yeah. Now, uh, it so happens that we want to reduce the number of uh, the number of data so that we can calculate better, so that we don't overfit. Overfitting, we will explain it later, is the no, is when the computer the algorithm has learned a particular data too well. So when we apply it to the or we apply it to data which we have not seen before, the computer might not uh, be able to predict it properly, because it has not seen because it has seen a particular data and has adapted only to that. So to reduce such cases and to make the calculations easier, we do pooling. So this is called max pooling. There are two types of pooling: one is average and one is max. So here we're convolving and taking the maximum. This is the second part. Once we did a convolution from that layer, we are doing a pooling, and this is max pooling here. Similarly, here we have taken the maximum and 0.33, 0.55, and so on. So what is happening is we are taking the maximum value, and that maximum value would point out to a certain feature. And even if there is some invariance, there are some differences in different pictures, it will be found. After we have used the pooling layer to reduce the spatial size, we are using normalization so that we can make the maths a bit easier for the computer and it is faster. Now, in convolutions, and these are not linear equations, not linear functions. So for such cases, we use activation functions to introduce non-linearity. So ReLU is one activation function which we'll discuss here. Every negative value has been reduced, like you can see, to 0. And we'll do it through the depth. A depth is the red, green, and blue. Uh, the whole stack will apply the activation function through the whole stack. Yeah, so in convolutions, uh, we are from an original image, we are doing a convolution, then we are performing an activation function, then taking the maximum or the average pooling. In this case, we did the maximum of the pooling, and the output of this becomes the original image for the next layer, and we perform a similar function. Yeah, and we keep repeating the process, and we have more layers. And if you want to learn a feature even better, we introduce more layers. Now here's a fully connected layer, which is before the final layer. A fully connected layer, as the name suggests, in this layer, every layer is connected to all the activations in the previous layer. And sometimes two fully connected layers are also used before the output. Now the computer here is learning, and later on it will use this data to predict where in which image was such numbers more, and will give a probability when it gives an output that a particular image is an X or an O. So if there's a chance that a particular number is more, represents zero more, so that goes for zero. How closer it is to a zero. Wait a second. I'm sorry. So here we can see the maths in a very basic term, very basic terminology points out to X that there is the numbers are more found, more closer to uh, what we see in when we convolve and do the pooling and function the activation functions. So that's average is zero point 0.9. So it points clearly X is what the numbers point to, and that is how it gets activated. Those neurons get excited and activated and uh, give the output. Yeah, so from the input to the output, these are called the hidden layers because we don't actually see them. And hidden, fully connected layers, sometimes we use two of them. So and their vote how the numbers and the activation functions, and what they are more pointing, what they point to, which image it points to more, decides what output they give, and they finally give a probability. So here you can see we have used plenty of uh, fully connected layers as well. We have performed uh, the convolution and activation functions many times. Now the output, the input and the weights, the voting which happens in the final fully connected layers, Now, if it has to learn, it sees what went wrong, and that's called back propagation in a very layman's term. And we back propagate and update the votes, okay, so that we can, learn. Uh, we would we would look at the equation as well, and uh, that's how the algorithm learns whether an image is right, what it has learned in the deep neural network. So the computer does the maths about how far, how wrong the right answer is, and what the actual answer is, how much it has, what it has gotten right and not, from its own learning and prediction. And backpropagation would correct uh, how wrong it has been. So here we can see, uh, as in this, we are discussing a very important topic here. In this, you know, uh, we have a curved line here. So as the weights are increased, the error is decreasing, and after that, after a certain point, it is again, as the weights are increased, the error is increasing. So we need to find a place where, after back propagating, when we are updating the the equations, where uh, the error is the least. We want to find those weights where the errors are least, and so we take steps, to find out where it is the minimum, and that's called gradient descent. And there are many ways of doing this. Stochastic gradient descent is one. Um, you know, the optimizer is what we use to update the weights. So hyperparameters are what, that part of the whole uh, neural network is what is in our control. So how much features, how many features we want to learn, how, what size pooling is, what size we want to, what size of the window we want to pool, and what size. So suppose we take a very big stride, so we might not be able to learn the features. Similarly, fully connected layers, how many number of neurons, how many fully connected layers we want to uh, have in the whole neural network, and how many times we want to iterate through all of that. That's in our hands, and those are called hyperparameters. I just skip a bit because I explained. So they tweak the hyperparameters. They're called, as in the video, it's called knobs, to see where you get the optimum result. So this is something which we tweak and learn while we make neural networks. And getting them well is very important for a successful in him. So this is something very basic we see. Was something. Never showed that. Now here we can see how the intensity of the color is different and how two pixels together would be closely related in a CNN. So as much complicated as it is, we need to tweak this hyperparameters to find the perfect CNN to predict. Here there's a analogy of text. We can skip it because that's we won't be doing text here. So yeah, so convolutions can work for spatial images. We don't use them otherwise. And if the data is not like an image, it is not no, space is not what is deciding the patterns, then we don't use that. This is the end of it, and we'll be now heading over to the slides by no uh, by Shova and Amini, Alexander Amini right now, and some of it we have discussed, some of it is new. I'll just share it. Yeah. So the computer sees an image as a number. We had discussed this previously. So here we have a picture of Abraham Lincoln, and you can see those images which are more close to white are closer to 255 and those images which are black are, let's say, like here it is completely black, it's 0 2. So that's how the intensity is displayed. Now the computer sees it as an array, of numbers. So here's a classification task. We are going to convolve over the image, find out the numbers. After convolving, activation functions, pooling, we can repeat it as many times and classify whether it is, you know uh, give a probability of whose photo it is. Now, as we get make more CNN, more layers and tweak the hyperparameters, we can find even high level features, and which are in the beginning of the CNN. With the first few layers, we can only find edges and corners. But as we make it more complex and keep adding layers after layers, the computer is able to learn and more complex features. So yeah, in the basic issue in computer vision is that not all images are same. It is not exactly the same image that you are searching for. So there is occlusion. A picture could be rotated. There could be spatial invariance, lighting. So we have to detect a particular feature which is more prominent in a particular image than others and differentiate based on that. So like I was explaining before, first few layers works for low level features, then mid level and high level can uh, find out a more complex image and differentiate it. So in fully connected neural networks, we have every neuron in every layer connected to the other neurons and layers. So this way we are able to find out the particular features in an image. So that is the X and that's the output. we had discussed this previously. The computer sees from an image, from a convolution, a small part of such values, and by convolving over them, here we have used, we have used a stride of two, and we can uh, create a new layer by sliding over through it. Yeah. We are using weights, an equation of y is equal to x c plus b. So wx plus b more appropriately. So w is the weights, the filter weights that we're using to get a feature, and after that we would be back propagating to find out the how what error we have. So in the beginning we are just doing multiplication and summation, and that's how we will proceed in a convolution. Have a kernel of size 4 by 4, and we are applying this in different places, and such an operation is called a convolution. We find out the features, we are multiplying as we had seen in the video to get a particular number, and share over the convolution where uh, the parameters are similar. Previously we had done this. So a computer, by performing convolution and by numbering blacks and white spaces here, can find out any shape, whether it is shrunk, shifted, that it's an X. Okay, so different features here which the computer has learnt, you know uh, shown in different colors: the X, the diagonal, the midpoint of the diagonal, etc. We have seen this particular operation before, and I think nobody would have any issue with connecting the dots here. So we're multiplying it. We have minus 1 and minus 1 gets 1, and so ultimately we have 9. And uh, so a convolution like that. So here's a 5 by 5 image and a 3 by 3 filter. By doing the convolution, we get 4 here in the feature map, and we keep stacking the feature maps. This is just one filter. We can have many filters for as complex the image is. So we keep adding the numbers here, uh, and finally we get, I'll just skip a bit because it's the same. We are convolving in different parts of the image. So we got 4 here, and then 3, and then 4 again, and then in the center we get 4. And after doing the multiplications element wise, and we add the inputs, and we get one feature map, which will be a convolution for the next layer. So here you can see different numbers mean different things here. So see, sharpen edge detect and a very strong edge detect has different numbers pointing out to the computer. So that's how features are extracted from an image. So it's a very nice representation of the CNN and the convolution happening for classification. Uh, so we have a kernel, it convolves over the feature maps. We have a stack of feature maps. We do the max pooling. We apply activation functions. We have a fully connected layer, or sometimes more than one, and then we give an output. So mostly in CNNs we are using ReLU. ReLU will make any negative value to uh, 0, and pooling is basically to reduce the size of the sample of each feature map, so that it is easier for the calculations and to reduce overfitting. So here's a demonstration of the maths when you use such uh, code here. So a neuron would have, in the hidden layer, it would have the input, it would have uh, you know, uh, multiplication with the weights, plus b is the bias that we have in, so that we can control some part of the equation. Yeah. So yeah. So y is equal to wx plus b. So here we have, for different locations, we have the multiplications, and then we activate it with a nonlinear function. So the width, the height, and the depth of the different layers, the different filters we have. Yeah, the number of filters is the depth here. The receptive field is where uh, we are convolving at a particular time. Then this is the code for it. We'll apply the ReLU function here, rectified linear unit. So any value below 0 is maxed to 0, and the values above 0 are what they are. So here we can see, after rectified linear uh, unit, that function, we can see there's only white values, and it's a bit easier to look at it as well, and find out the features. So to reduce the size, to also deal with spatial invariance where there are some differences, we are doing pooling here. So we are taking the max value from this convolution, then this convolution, which is 6, 8, 4, and 3. So this solves the question of how to downsample, how to preserve, the variance. What we saw earlier, that you could see a rotated images also being detected. How to reduce overfitting. So all that is thanks to pooling, average pooling and max pooling. So here you can see, as we have more convolution layers, in the beginning only the edges and dark spots are found, then more objects are found, and then we have the whole facial feature being detected by the convolution layer. Now here we have a softmax function at the end. I've uh, explained the previous functions before. The softmax function at the end is what gives a probability from 0 to 1 of each uh, label that we have, whether it is, each prediction that we want to do. So let's say a prediction of car is zero point 0.2, a prediction of truck is zero point 0.3, and we sum it, it will give 1. So in all these layers, we are learning the features of the image, and here we are performing the classification. Here's the equation and formula for softmax. Basically, the summation of all the labels will give us 1, and after pooling, we are flattening mm, the end product of the last convolution layers, so that it is just numbers at the end, and then we can apply use the softmax function. So here's the code for it. We'll be doing it in code later. So um, we have the first convolution layers. We are using keras and TensorFlow here. So this is a conv 2D code for that. This is the filter size, which is 3 by 3, pool size 2 by 2. They've written as 3 and 2, and strides of 2. The images size is 32 by 32, and then uh, applying ReLU function. Similarly, for the second convolution layer, it is we have uh, filter size of 3 by 3, and rest everything is same. So and we are doing max pooling, so we are taking the maximum value only from each convolution. After flattening, we have a greater number from which we that's 1024, and we have flattened the image. It is no longer in it is 1D that we have, and then from that we are uh, classifying into different outputs. So this is learned used in semantic segmentation, robot control, object detection. So here we can see the cancer can be detected. It can be missed by a radiologist, but the AI can find it. Here we can see the outlines of two animals, two cows here. So we have downsampled and then later upsampled so that we can you know, uh, classify. So see the cars can navigate uh, with the help of computer vision and convolutional neural networks. Once the AI sees that there are three paths that you can take, the GPS would give you which way you want to go and which path you have to take. All of this is possible without human control. You can see the convolutions are then flattened, and then through fully connected layers you can see which path you can take, and then it is sent back to the uh, computer. And in the GPS you have this car turning right, and then we are giving an output here. It is used in many things, and we have covered some of them here. Now Sherwin Amidi has another representation of what we are doing in computer vision and how we are uh, with equations, how we have uh, convolved over each image, used tooling, etc. So we'll go through that. We'll spend some time on that, and after that we'll go through the code. So I hope we do it on time. Yeah. So this is Shavine Amidi and Ashwin Amidi's cheat sheet. We've discussed before. So we have an image of a teddy bear. We convolve over different parts of it. We have a book here. We pull it, and then fully connected layers will give us the fully connected layer is the second last, or sometimes we use two layers, and then we'll go through the software function. And the different hyperparameters can be controlled so that we can succeed in our CNN. Here you can see uh, how the convolution is convolving and giving a map here. The filter size is 3 by 3, and we have a stride of 1 here. So the output in the beginning till is called feature map, over which we convolve again, and keep convolving till the time the output the desired result is achieved. So I had discussed two types of pooling mostly. Max pooling we had seen before. We're taking the max. If here the image is most dark in the top left, so that's what we use. It's a maximum value. So the detected features are preserved, and in average, we're taking the average value of the intensity. So whatever numbers are there, we add them up and we average them. So here we are used the average value here. So the end result is we do flattening and then fully connected layer. That output, the end of the flattened input goes to the that output goes to the fully connected layer, and each input is connected to all the neurons of the flattened layer, and we can optimize the probability, the score that uh, the network gives. So C channels for colored images, it is RGB, so that's 3, and filter we have discussed before. So this is the original image, and we go through a convolution, and C is the number of channels, and we get a feature map of size f by f into C into K. So that's filter K is the number of filters we are using, not the size. Yeah, I had discussed before. Stride is how many number of pixels we are moving. So in the previous cases, we have seen 1 and 2. Sometimes mostly 2 is also used, and we can use 1 if you want to learn more features. Yeah, another important thing which we have not discussed right till now is zero padding. Now, uh, if we want to go through all of the features, we want the convolution to have more dimensions. We want the convolution to take in more features, not skip out the end parts of it. So we add uh, zero layers with zero here. So the end parts of the layers are uh, the parts which are gray here are zeros, and that's called zero padding here. Give me a second, please. Okay. So if we did the 3 by 3 kernel operation at a point, it would at a point where at the edge we would not be able to get the data from the uh, paths which are not zero padded. That is why we apply zero padding, so that if we want, so that we can have the same dimensions as the input, so that we can preserve the spatial dimensions also by doing this. So here you can see that by doing this, we can preserve the spatial dimensions. If we didn't, like, let's say when the padding is 0, we cannot convolve at the edge of it. So by doing this, we have put in zeros here, and we can convolve here. We are able to see the input more clearly end to end, and the formula for the padding is provided here. That's filter and stride. So we are subtracting stride from the filter, and from the I from this stride we are subtracting the um, from the uh, bigger picture, we are subtracting the I also, and then dividing by 2. Another easier to understand formula, I'll just let you know. Yeah, that's let's say for the height minus uh, the filter plus 2 times the padding divided by stride plus 1. So that's another equation. That's an easier to understand equation. So if the image is a square, we have the weights. That's just one part of it, because weights into weights. If it is a square, minus the filter uh, plus the 2 times of the padding that we're doing divided by stride plus 1. Sorry, the different types of neural networks is discussed here. So we had discussed some hyperparameters before, and we can tweak the hyperparameters to get the desired result. So at different parts, we have different parameters and different outputs, and we need to tweak them to succeed in this. So here we have the formula. It is uh, the receptive field is k here, and by performing this function where f is the filter size and s is the stride value, we can get the value of the receptive field. Let's say 5 here. So mostly I discussed the ReLU function is used, which gives a value from 0 to z. Sometimes leaky ReLU is used, but mostly we have at a particular level used ReLU only. Softmax function I've discussed, it gives a value which adds up to 1. So the value of 10 values would give 1. So object detection, this is image classification where we're just classifying what the image is. So we are localizing the images here, and in detection we are detecting that the above part is teddy bear and below part is book, and you know different CNNs are used for this purpose. We will not be covering that. So I think we have discussed quite a lot here, and now we can do some code for the same. Uh, but before that, we'll quickly go over through a slide. If you have time, I'll see if we. I'll show you parts, how the overfitting is and how we correct it. Yeah, so here you can see there's a diagram telling us about overfitting and underfitting. Now, why is the labels? So when we have a model fitted, here the model is not, the X line is not completely predicting uh, the output. We see that there are errors and it is not learning the output well. So that's called underfitting. And same thing. So in overfitting, the model has learned all the values in the training data. So there is very low there is very low error in the training. So what happens when we do it to data which is not seen, it will give a large error. What we want to do is we want to reduce the overfitting by making the computer learn the training data a bit less accurately, and for that we use dropout, regularization. I'll discuss that, and we use such techniques. Okay, and pooling and all. So yeah, so there's a large data error there. So to strike a balance, we have some ways to mitigate this issue, like regularization. I'll discuss that later. Dropouts, we reducing randomly some neurons during the training. So we'll watch a video for regularization. This video is by 2-minute papers, and I hope you enjoy this.
know what the scariest thing in the world is?
Scholars, this is 2-minute papers with Károly Zsolnai Fehér. In machine learning, we often encounter classification problems where we have to decide whether an image depicts a dog or a cat. We'll have an intuitive but simplified example where we imagine that the red dots represent dogs and the green ones are the cats. We first start learning on a training set, which means that we get a bunch of images that are points on this plane, and from these points we try to paint the parts of the plane red and green. This way we can specify which regions correspond to the concept of dogs and cats. And after that, we'll get new points that we don't know anything about, and we'll ask the algorithm, for instance, a neural network, to classify these unknown images so it tells us whether it thinks that it is a dog or a cat. This is what we call a test set. We have had lots of fun with neural networks and deep learning in previous 2-minute papers episodes. I've put some links in the description box, check them out. In this example, it is reasonably easy to tell that the reds roughly correspond to the left and greens. However, if we just jumped on the deep learning hype train and don't know much about neural networks, we may get extremely poor results like this. What we see here is the problem of overfitting. Overfitting means that our beloved neural network does not learn the concept of dogs or cats, it just tries to adapt as much as possible to the training set. As an intuition, think of poorly made real-life exams. We have a textbook where we can practice with exercises, so this textbook is our training set. Our test set is the exam. The goal is to learn from the textbook and obtain knowledge that proves to be useful at the exam. Overfitting means that we simply memorize parts of the textbook instead of obtaining real knowledge. If you're on page 5 and you see a bus, then the right answer is B. Memorizing patterns like this is not real learning. The worst case is if the exam questions are also from the textbook, because you can get a great grade just by overfitting. So this kind of overfitting has been a big looming problem in many education systems. Now the question is, which kind of neural network do we want? Something that works like a lazy student, or one that can learn many complicated concepts? If we are aiming for the latter, we have to combat overfitting, which is the bane of so many machine learning techniques. Now, there's several ways of doing that, but today we're going to talk about one possible solution by the name L1 and L2 regularization. The intuition of our problem is that
So what he has discussed is what we have also seen in our academic life, that sometimes we have the question paper exactly from the book, and we don't have to use our brains, we don't have to understand things, we just have to give answers, and that doesn't really train us to become better students or learn how to think. So that's called overfitting, in that context. And uh, the aim is that we think that we are able to adapt to new questions, and that's why we want to reduce the overfitting so that we can do well. Because if we get a question which is out of syllabus, we'll panic.
the deeper and bigger neural networks we train, the more potent they are, but at the same time, they get more prone to overfitting. The smarter the student is, the more patterns he can memorize. One solution is to hurl a smaller neural network at the problem. If this smaller version is powerful enough to take on the problem, we're good. A student who cannot afford to memorize all the examples is forced to learn the actual underlying concepts. However, it is very possible that this smaller neural network is not powerful enough to solve the problem, so we need to use a bigger one. But bigger network, more overfitting. Damn, so what do we do? And here is where L1 and L2 regularization comes to save the day. It is a tool to favor simpler models instead of complicated ones. The idea is that the simpler the model is, the better it transfers the textbook knowledge to the exam, and that's exactly what we're looking for.
So we add a penalty to how the model is, and that is how we are regularizing the model.
Here you see images of the same network with different regularization strengths. The first one barely helps anything, and as you can see, overfitting is still rampant. We With a stronger L2 regularization, you see that the model is simplified substantially and is likely to perform better on the exam. However, if we add more regularization, it might be that we simplify the model too much, and it is almost the same as a smaller neural network that is not powerful enough to grasp the underlying concepts of the exam. Keep your neural network as simple as possible, but not simpler. One has to find the right balance, which is an art by itself, and it shows that training deep neural networks takes a bit of expertise. It is more than just a plug-and-play tool that solves every problem by magic. If you want to play with the neural networks you've seen in this video, just click on the link in the description box. I hope you'll have at least as much fun with it as
So here we got some intuition about uh, overfitting and regularization, and we would be applying that later as well. So what happens is the error we add the L1 and L2 regularization to the weights. To the error, we have some weights, and uh, we multiply it with the regularization uh, value. So that's a hyperparameter value represented by lambda. So let's say there's a loss function. So it's loss function plus lambda into w. So L1 regularization is where we're taking the absolute value of the weights. So if the weight is, let's say, -1, it is reduced to 0. And because L1 regularization would want to uh, will punish the weights which are close to, penalize it which are close to 0, and make them 0. So the maths can get a bit tricky here. And L2 regularization, it would be, let's say, mean square error plus uh, yeah, mean square error plus lambda, and lambda into the square of the weights. So it is penalizing it to 0, but not to 0 itself. So in such a way, we can control the training, we can control the neural network during training itself, and we'll do some code for that. Um, yeah, about metrics, that's another important thing. You would be whenever you run CNNs, you would find uh, the output, and along with it some information, and those are the metrics with which we can judge how good our neural network was. I'll just show you an example. Yeah, here we have uh, here we have seen that at the end we have precision, recall, F1 score, and support written, and that's these are the metrics of a particular, yeah, of the data that we just ran uh, the whole code and the output of it. So precision is the the true positives divided by the true number of false positives. So the amount let's say for the airplane, how many times the uh, computer found the true positive, the algorithm found that it is an aeroplane and it was right, divided by the times it found it is right and plus the times that it was not right. So that is the precision. F score is the harmonic mean of the precision and the recall. And the recall is the number of times it found that it is. Please give me a second. So I'll just come back to recall later. Precision is we are finding the ability of the classification model to find the relevant data points only. And this is how we evaluate the model and how we are classifying how well it is going. So I'll show you a confusion matrix as well so that we can understand true positives and negatives. See, ability of a model to find the relevant cases within a data set. So that's called recall. It is the number of true positives divided by the number of true positives plus the number of false positives. So all the airplanes which were correctly found plus the number of those which were not airplanes is what recall is. And I'll just show you the formula for F1 score. Yeah. So we are taking the harmonic mean of the precision and recall, and I'll tell you the reason for it in a while. So F1 is 2 into precision into recall plus divided by precision and recall. So between what is relevant in the data set and what has been correctly predicted, there is a trade-off between the precision and recall. So we are using F1 because we want to have the trade-off, and that is why we are taking the harmonic mean as the F1 score. So any value which is uh, so if you want to find a blend of the precision and recall, we are combining it using F1 score, and lower values are reduced, are not counted in F1 scores. And yeah, the true positives and false negatives and etc., which I was discussing, I'll just show you. Just give me a second, please. Yeah. So here you can see. So there are true positives which are predicted and are really positive, like a plane which is a really a plane, and the algorithm has also predicted as a plane, and something which has been predicted as a plane but is not, something which has been predicted correctly as not a plane and is not a plane, and some aeroplane or anything, and something which has been predicted as a plane but is not a plane but is actually an aeroplane. So that's a wrong prediction, and uh, that's what the true positives and negatives, etc. are. So we have true positives, negatives. Let's now do some code for the same. Do some basic code, and we'll keep seeing what we can tweak and what we can learn from that. In the chat, I'll uh, share with you the code what we are going to go through right now. I'll just load it and tell you. Please click on this link so we can do some classification. We can see our convolutions. Yeah, and I'll show it to you on my screen. Yeah, so once you have clicked on that, you'll find you know, image classifying images of cloth. So we can, it's an easier to understand, and there's good description already given here. So we'll be doing another code later. I hope you have reached at that. Uh, you have opened the link and yeah. So we are using Keras, which is a high-level API to train and build models in TensorFlow. So this data set, it's the fashion MNIST data set. So we have 70,000, yeah, 70,000 grayscale images in 10 categories like sneakers, shirts, etc. And the images are 28 by 28 pixels. So the sneakers shots are the labels, and the 70,000 images are the uh, what we'll train and test on. So we can simply run this, and okay, somebody's saying we didn't get any link. I've put a link in the chat here. Just let me know on the chat if you can see any link, or if that is also not possible. On the screen itself, I'll share a smaller I mean a smaller link for the same. Okay, yeah, yeah, it's there. Yeah, so we can just run it. It will give us the TensorFlow version and import some libraries. So this is a bit cooler than the hand digits classification we had. So we are using 60% images for training and 10,000 for testing. This is the code to import it. Very easy, just run it. The training images uh, and the train labels are the training set, and similarly the test images and test labels. I think everybody would easily understand this. Yeah, so pixel values, close to white is 255, or white is 255, black is 0. The labels are labeled from 0 to 1 in this way. So 4 would be coat, 9 would be ankle boot, etc. So we are storing the class names like this. So yeah, let's see what shape the images are in. So it's 60,000 images, 28 by 28. That would be 10. Sorry, 60,000. That are the number of labels, and this would be the 10 arrays. So an array of 10 actually, not 10 arrays. And the 10,000 by 28 into 28, and yeah, and 10,000 test labels. And if you want to see test labels, we have to first see that it is pre-processed correctly and it is in 0 to 255. Here you can see more intense is 255 and black is 0. And you can tweak it for, let's say, something else. This is a quote, I think. And from here you can see what we're calling. So that would be a pullover. We want to scale them from 0 to 1, which is why we are doing a division operation here. Let's see how the first 25 images are, or we'll make it. Let's have it first 30 images are. Oops. Oh yeah, it has to be less than that. 13 images are. Yeah, so we can see the first few images here: pullover, sneaker, etc. So here's the code for it. We are flattening it, the input shape, and then we'll compile it later. And this is the last layer, and we are also using ReLU activation function. So we are flattening it so that the array of two 28 by 28 is a flattened one dimension from 2D to 1D. And then we are using dense layers or fully connected layers, and we are running that so that we can mm, uh, finally get the output in the form of 10 uh, logit arrays of length 10. So we are using the loss function categorical cross entropy. Two labels we use this, and matrix would be accuracy, which I had described earlier, and RDM optimizer. So how the loss function is optimized, and anytime you have any like what an Adam optimizer is, or you want to tweak things, you can Google and do that. So we'll train the model. We have fit in the training images, test images, and we'll run it for 10 epochs.
Shashank, I guess we are not able to see your screen, the
Oh,
code. It's
oh,
at the first few lines of code import TensorFlow STF. Could you kindly
yeah,
check
yeah,
once?
yeah. I just saw that. Yeah, which is not right at all. I'm so sorry. But can you see this?
Just a second, it's loading. Yeah, yeah, yeah. Perfect, perfect.
Yeah. So here we ran all this. So I'll just tell you. We got the shapes, lens, labels, etc. Just keep running this, and the labels will give us the digits from 0 to 9, which you can check from here. You can tweak it a bit, like I'll just show you. Here you can put in 6 and run, and so now we're getting sneakers here because that's we should get shirt here. I don't know why. Wait, if we yeah, because it starts from 0. So this is a shirt. Yeah. So you can tweak that or pull over. Okay. We'll not worry about that. We are dividing it by 255 because I hope you are running it. So we can divide it by 255 so that we can normalize it to 0 and 1. So I chose 13 here as the numbers to display, and input shape of 28 by 28 flattened to one. You know, uh, we'll flatten it to 784, and then a dense layer of 128, and then a connected layer again, which will give us 10 audits around here. Yeah, so I ran my code, and you can see the accuracy with every epoch increases and the loss decreases. So we're getting a 90% accuracy. What we can also do is tweak it a bit. Let's say we use this will give an error. No, this will not look good. We can even get it better accuracy. So yeah. So when we evaluated it, I will go to that later if we have time. When we evaluated the test loss and test accuracy of the model that we made, we get a test image of that we have put in the test images and test labels. We are getting uh, accuracy which is less, very less than uh, what was on the training data. This means that it has overfitted, and that is what we had previously seen how to use regularization. We'll do that code as well. So you can play around with the data. You can see if we can uh, get a different accuracy in the training itself, just to see how it goes. And here we are getting um, the predictions for different overall 10 predictions, and the maximum value we'll find it is for 2. So prediction of 2 is prediction of the first one is 2, it says. So it says that it is 9, which is the class name 9. 2 would be 0, 1, 2, and that's 9. So we can have a look at the full 10 class predictions. Yeah, that's a boot, but it has wrongly predicted it. So we can keep tweaking it with it, and this is one model. I'll share with you another one. Screen share. I'll just share the link. Or it's taking time, or I'll just please hang in there. Yeah. Okay. Few minutes so that we can do some regularization as well later. Provided a link now, so you can. Yeah, I've provided a link, so now you can have a look at a conv that we'll do, which is simpler. Okay, you can read the relevant part. I hope we are all on the same page. I'll just share my screen. This link, somebody asked. This link is for you know uh, some code that we have. Okay, another 15 minutes. How Vivek is asking. So yeah, we'll move ahead. So we've imported the Keras and had a look at the version. Now we'll import the libraries and layers. And so here we're adding in layers. So layers, convolution 2D, 3 by 3 kernel activation relu. Input shape is 28 by 28 because we're taking MNIST. Uh, yes, we'll do max pooling 2 by 2. Then we have convolution that's 3 by 3 into 64. Uh, and then activation is same, and we'll do again max pooling, again the same thing. So we had the convolution layers that's 32 and 64, and we'll flatten it and uh, apply activation functions and softmax, and let's see how it is. Here you see it was flattened. So now what we'll do is we'll train it on the MNIST. Okay, yeah. So we have training images which are reshaped in this way. We are loading in the data and reshaping it, normalizing it, and uh, we're using two categoricals so that we can uh, uh, the labels are one hot encoded. So you can run this and see. The code will take time. So meanwhile, we'll do the regularization as well.
Shashank, I guess until the code runs, we can explain the next few lines of code.
Okay, and yeah. So after that, we'll be, what I'll do is I'll reduce the epochs. Okay, no, let it run then. I'll also share on the link. So after that, we are evaluating how the model worked and what accuracy we achieved. So I'll very soon share with you another code. And, okay, this one is on the MNIST fashion dataset. So this is the MNIST which we had seen earlier, which I'll just share with you. I'm so sorry, this is taking time. I'll what I'll do rather is I'll share with you the link, which is even better. Yeah. So here's the link for the regularization code, and since somebody wants to go and there is we have less time for some people, we can go to this link like here, and you can copy the code and run it. I it's wrong somewhere, and yeah, please head on to this link that I've shared. Okay, we'll be uh, using optimizers, and we'll also be using L1, L2. So that will that can also help you understand. Thank you for your patience, everyone. Yeah, so here you can see the accuracy has improved, and uh, it gives us good accuracy. So that was training a convolution. What you can do is you can play around with the data. You can change activation functions if you want, or add more dense layers, change the size of the kernel and all. Let's say we do a 2 by 2 kernel, 1 by 1, let's say. So that is the way to learn certain things in this field. This we can do on ourselves, and uh, let's head over to the code that I had shared in the chat box. So that's the code running for 2 epochs. So here we see the accuracy is around 60%, 66.66. Okay. So what we can do is we can, let's say we add we the learning rate is how many steps the gradient descent is taking, at what rate the gradient descent is moving. So we can change the learning rate. If it is too large, it will not be, it will skip. If it is too small, mostly 0.01 is used. If it is too small, it will take a lot of time. So that's another hyperparameter. It controls the size of our gradient descent step. Okay, so let's run it. It was 0.66 with this. What else we can do is we can change these functions as well. We can use different values for L1 and L2 and see how it goes then. See, here we have used a lesser learning rate, so we have more accuracy. If our learning rate is big, it will give the accuracy will suffer. See, we can already see the accuracy is suffering. Now the accuracy will, I think, be fine. Yeah, what we were planning to do is right now remove this. We have changed the regularization, so we'll again get a different value. It was 0.66 in the beginning, and let's just see what values we get with different learning rates and different regularization. Sorry. So these are the values of the lambda that we have. So we don't get good accuracy with this. Our learning rate we have kept fine. Let's make it lesser and see. See, now the accuracy has improved tremendously because we are using a low value for L1, L2, L2. So it will have less of impact, less penalties, and now it has improved here. So you can use this. So from here, all you had to do was copy paste. I'm so sorry, I did not explain. You had to copy and paste the code and just run it from this uh, blog post that I shared with you. Now we'll do another one. I'll stop the screen share for a second. I've provided a link here. Now, one important thing with the link is to please download a particular file which I'll share. It is in the GitHub as well, and I'm sharing it here as well, and upload it in um, the uh, the collab that you run this on. That particular file, I'll link it. sources. I will link it again. Yeah. This particular file that I've sent, the kr helper funcs.py, uh, upload it in the folder. You can do an ls command and see where you are, and upload it in the folder where you are currently at, so that you can run the code given here. Um,
Shashank, I feel we have taken a lot of time, so I guess we should head over to some questions now.
I'll just share with you my screen also. Yeah, yeah. Please tell me.
Uh, so I was telling that I guess we have taken a
Yeah.
lot of time, so we should head over to the questions now, and I guess conclude of this session. So should I start taking the questions, Shashank? Sorry, could you unmute yourselves? Shashank, you're not audible. I guess you have muted your mic in the StreamYard.
So sorry. Yeah. So I
Yeah.
need to go through the questions here and tell you.
Yeah. Okay. So I'll
Okay.
be reading out the questions. So we have.
Okay.
Mm, mm. So when to use max pool and when to use
Max
average pool?
pool. Okay. So mostly we have been using max pooling only, and we use that. And more specifically, max pooling is average pooling, which we don't use so much, is when we want to have less features, less data in the feature map. We we don't want to predict things more accurately. So that's where we are averaging the values, where we don't want the features to the high level features are not there. That's where we're using average pooling, and mostly otherwise we use max pooling.
Yeah. 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 So moving on to the next question, we have. Uh, Okay, so Mayank Madan had this question for us, for me actually, like, will GANs be covered in the course? Mayank will be having another session upcoming where we'll be covering computer vision in depth, so stay tuned in for that. All right, so moving on to the next question. Today we learned, okay. So,
Normalization.
what is a fully connected network?
I had in fully connected network, every when the neurons from the previous layer are connected to the next one. I mean, it is flattened, and then everything is the neurons are connected from the previous to the end. So that's a fully connected. Yeah.
Okay. That's cool. So what exactly was that matrix that showed up that you were trying to explain during the start of the session? That was also a question.
Uh, the matrix that I was, I mean, there's a smaller matrix and a bigger matrix. The smaller
So I
matrix
guess
will,
they were asking of both matrices that were shown up. I guess they are talking in context of images. I guess some were not knowing that images are in form of matrix, I guess.
yeah, yeah, images are in form of numbers, and the smaller images is the kernel, and uh, yeah, and the bigger images is the input that we are convolving over and adding.
Okay. So we have one last question in for the day. What is data augmentation?
Okay. When we are tweaking, the images, so that we can increase the the size of the training set, basically. Sometimes it is done when we don't have enough data. So we can manipulate it by shifting, by zooming into a data. So we are actually by doing this getting more information about the training data, and which is more relevant. So the different types of like zooming and flipping, etc. So
Okay,
the invariance is helped because of this. Yeah.
okay, okay. So we have one question that just came up. Will deep learning surpass human intelligence?
We all are wondering. In some cases, deep learning has the level of intelligence for like AlphaGo, and uh, uh, s- that game has been, the grandmaster had left that game. I know chess masters. Deep learning has defeated chess grandmasters as well. So in some ways, deep learning has surpassed the common human intelligence that we see. It has in some cases, but for certain things, it has not. Yeah. So we are making progress in that. Few years ago, we were not here. So yeah, thank you.
All right. So thank you so much, Shashank. We feel really great for having you along the session today. We
It was
hope
a
that
pleasure. Thank you
audience
very
wouldn't
much.
have enjoyed today. I guess it was a lot of maths. So no one loves maths, be it engineers or be it someone else. So we are really sorry for everyone to like keeping you guys bored in case you guys felt bored. But maths is an integral part of deep learning, and everybody has to accept that kind of fact of thing that deep learning has maths. So stay tuned for tomorrow's session because this was the only mathematical topic that we had to be covered. And in tomorrow's session, we are gonna have topics like image segmentation and some parts of object detection, which will be covered up by Aniket Thomas. So stay tuned for those guys. So Shashank, say bye bye to everyone and thank you.